Chapter 2, Process Flows. There are three keywords of this chapter: variables to characterize chemical processes. The second one is diagrams to describe chemical processes. And the last one is balances to calculate quantities for processes. Here is summary of what kind of things you can learn from this chapter 2. Let me read them. What are the important process variables? So this is the first keyword. And what are the four major processing units common to most chemical processes? What are three different ways to diagram a process flow sheet? Which diagram is used for which purpose? This is the second keyword here. And four major processing units are required for making this diagram. How do I begin to synthesize a process flow sheet? How are process flow rates and compositions calculated? By using balance equations, you could calculate something, and flow rate and compositions is used to describe processes in diagrams. What kind of information is useful for completing process flow calculations? How do I know I have just enough information to calculate process flow? This last question is related to degree of freedom. So let's go to the body of chapter 2. The first one is about the process flow sheet and or flow diagrams. So this is an example for flow diagrams. The box indicates some process units or process operations, and the arrow is material transfer. So let me try to trace these arrows. Raw materials are introduced into feed preparation, and then we could make some reactants from the raw materials. And the the reactant is introduced into chemical reactors. Of course, there are some reactions inside of reactors. Then we could have some products. In these product streamlines, you can find several things. Product, of course, desired product, I mean, and also remaining reactants, also plus byproducts. So we should separate the desired products from the others. So the next thing we need to have is separation unit. So separation unit have two different streams. One is going for desired products. The other is going for waste products. So let me follow this line, and then the desired product is transferred to product formulation unit or storage, and then the final product is going to customers. Or the waste product is going to environmental control facilities, and then with some treatment, these wastes are discharged into environment. This is the very simple process flow sheet, or we can say flow diagrams. Let me write down. I prefer flow diagrams. Flow diagrams. Flow diagrams. Also, actually, in the real flow diagram, you have more information should be involved. Some rate of raw materials, or sometimes the composition of raw materials or something like that. Also, plus, you could have some material transfer equipment in this flow diagram, like a pump. The other thing is energy transfer equipment, like a heater. So, with this kind of information, you can complete this process flow sheet or flow diagrams. Okay, so there are a lot of things required for completing the flow diagrams, and the first thing we need to have is process variables. Let me change the pen into laser pointer. Process variables. So here we have four different process variables: number related variables, and pressure, temperature, volume related variables, and time related variables. So let me write down some ideal gas law here. P V is equal to some amount constant, ideal gas constant, and T. So P, V, and T are the variables to define the processes. So the first one is, actually let me start with N, number or moles. So number related variables include moles, mass, composition, concentration. The first two, including moles and mass, are extensive variables, and the other thing, composition, concentration, are the intensive variables. The next thing is pressure and temperature are process variables. Also, the last one in the ideal gas law is volume. Volume related variables include, of course, volume and also density. Density is the mass per volume. Okay, that's it. And also plus one more thing, time. Time related variables are used for making the flow diagrams. For example, flow rate. Let me write down some unit of flow rate. Like volumetric flow rate is cubic centimeter per second, something like that. This is the flow rate, and here is the time term. Let's go to next item, dimension and unit. The process variables have dimension and unit. Also, we should know the difference between dimension and unit. What is the dimension? Dimension is the fundamental quantity of a physical entity. Fundamental quantity. And unit. Dimension have units, specific magnitude of a dimension. So here is some example, and then you can understand what the difference between dimension and unit is. Here are 5 base dimensions: mass represented by m, length represented by l, time represented by t, temperature represented by capital T, and amount of substance represented by capital N. So let me start with M. Mass. M is the base unit, including kilogram, gram, ounce, ton as unit. So mass is dimension, and mass could have various units like that. Length, L, is the dimension, having the units of meter, foot, centimeter, mile. Time, small t, day, hour, second. Capital T, which is the temperature, having degrees Celsius, degree Fahrenheit, blah 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 blah. Another thing is N, number. So gram mole, kilogram mole, ton mole. So we have 5 base dimensions, and each base dimension cannot describe the other dimension. And also each dimension have various units. Okay, so I have said about just 5 base dimension. How about area? How about the other physical entity? For example, area. Area is non-based dimension. So this non-based dimension can be described by base dimension among or combination of base dimensions. So for example, area could be represented by L square. L is the base dimension. However, area is not the base dimension, so it can be described by some base dimension, L square. Let me think about pressure. Pressure is equal to force per area, and force is described by mass, by acceleration. And then what is the acceleration? Acceleration is um, length by time square, and also this is the area is the L square. So the dimension of pressure is described by the combination of base units like mass, this is m, mass per L here per t square. So again, non-base dimensions could be described by a combination of base dimension. Okay, so from now on, I will explain about each process variables, number related variables, and pressure and temperature, volume related variables, and time related variables. The first one is number related or n-related variables. The number related variables include mass and moles. The popular unit of mass is pound, 1 pound, or 1 gram, or 1 kilogram, or and so on. 1 pound is 453.592 gram. The symbol of pound is lb. Actually, lb comes from an ancient Roman unit, libra. Libra means balance. The next one is moles. 1 pound mole is 453.592 gram mole, or sometimes called just mole. So this is the same value because pound is going to gram. You know what does the moles mean? The mole is the number of groups containing 6.02 by 10 to the 23 atoms or molecules. Sometimes we should convert mass to mole or vice versa. The quantity is used for those kind of conversion is molar mass, or sometimes called molecular weight, large M. The conversion factor to convert moles to mass is molecular weight, so something like that. Mass of species I is equal to moles of species I by molecular weight of that species. Unit? Gram per mole. How to calculate total moles of an element in a given number of moles of a compound is here. Let me give you an example. We have 3 mole of carbon dioxide, and the number of oxygen in 3 mole of carbon dioxide is number of oxygen in 1 mole of CO2 by number of CO2 molecules. So the first term is going to here. Right now we have 2 more oxygen atom in CO2. So the unit of the first term is mole oxygen atom in 1 mole CO2. By we have right now 3 mole of CO2. So 3 mole CO2. After removing more CO2 and more CO2 from the first term and second term, which is going to 6 more oxygen atom. It's very easy. One more number related variable is here. That is the composition. Composition is described by sometimes mass fraction or sometimes mole fraction. Here's the definition of mass fraction and mole fraction. Mole fraction, no. Mass fraction of species I is equal to mass of species I per the summation of all of mass of all species I. That is to say, m subscript I per overall mass. Or mole fraction is described in the same way, but in terms of moles. Mole of species I per the summation of moles of all species I. Of course, the summation of all mass fraction and all mole fraction should be equal to 1. How to convert the mass fraction from mole fraction or vice versa? Here's the equations, but equations are not very important thing. I'll give you how to convert between mass fraction and mole fraction in the following example. Example number 1. We have 12 gram of glucose and 3 gram of sodium chloride are dissolved in 85 gram of water. Molar masses are 180 for glucose, 58.5 for sodium chloride, and 18 gram per gram mole for water, respectively. So let me try to calculate the mass fraction of glucose here. Of course, in the numerator, we have 12 gram glucose per, and then it's time to sum all of materials involved in this solution. 12 gram glucose, 3 gram sodium chloride, plus 85 gram of water, then 0.12. So I can say the mass fraction of glucose is 0.12 or sometimes 12 mass percent. How about mole fraction of glucose? Almost similar. Right now, glucose in the numerator and in the denominator, glucose plus sodium chloride plus water. But you should convert the gram into mole. It's time to use molecular weight of each species. So 12 gram glucose per each molecular weight is going to gram mole. Okay? The other species should have the same operation. How about sodium chloride? Which is 3 gram sodium chloride per each molecular weight. Water, the same. So the resultant answer is 0.014. I can say the mole fraction of glucose is 1.4% mole fraction. Let's go to the example 2 right now. 12 gram mole of glucose. At this time, I have the information about the moles, and 3 gram mole of sodium chloride are dissolved in 85 gram mole of water. Actually, the same example. So, it is very easy to calculate the mole fraction of glucose because we could use the information presented in the example 2. So something like that. How about mass fraction? In this time, we should convert gram mole into gram by using the molecular weight. So right now, you should multiply the corresponding molecular weight to the mass. In this case, molecular weight is multiplied to the mass. So let me check the unit. Gram mole glucose, gram mole glucose. So finally you could get gram. The same operation is going to sodium chloride, also water. Then finally you could obtain 0.56 as the answer, or which is equivalent to the 56 mass percent by multiplying 100 number. That's it. The second category of process variables are in this slide temperature and pressure. We have 4 different temperature units: Kelvin, Rankine, Celsius, Fahrenheit. Those units are converted to each other by using those equations. Don't memorize them. So I'll give you the equations if you have found this kind of conversion in your examination. Room temperature is equal to 25 Celsius degree. Degree Celsius is equal to 77 degree Fahrenheit is equal to 298.15 Kelvin. When we are using the Kelvin, we want to use degree, which is equal to 536.67 degree Rankine. You are no. Okay, here. So Celsius and Fahrenheit could be considered as the daily units. So we are using them in our daily lives. However, Kelvin and Rankine can be classified as the absolute units because they are starting from the zero absolute temperature. You are very accustomed to degrees Celsius or Celsius temperature or centigrade. The Celsius temperature is based on the properties of water. Here is the freezing point of water, and at the other point you can find the boiling point of water. The temperature difference between boiling and freezing points are divided by 100. That is the unit scale of Celsius temperature. Kelvin have the same unit temperature scale. Let me check the temperature difference between the boiling and freezing point. So 373 minus 273, exactly 100. So Celsius and Kelvin have the same unit temperature scale. However, the starting points are different. Of course, I have said again, Kelvin starts from 0. However, Celsius starts from minus 27.3. Fahrenheit degree are popularly used in British and also USA. So 0 Celsius degree as the freezing point of water is 32 degree Fahrenheit. The boiling point of water is measured at 212 degree Fahrenheit. So let me get the temperature difference, those 2 points, 180. So the unit scale of Fahrenheit is smaller than the unit scale of Celsius. That is to say, delta 1 Fahrenheit is smaller than delta 1 Celsius. Let's go to the final temperature ranking. The temperature difference between boiling and freezing is the same as the Fahrenheit. 672 minus 492 is 180 and also 180. But starting point is different. Rankine starts from 0, of course, because it is the absolute temperature. However, the starting point of Fahrenheit is minus 460. So the relationship between Fahrenheit and Rankine is very similar to the relationship between Celsius and Kelvin. Those four things are the temperature variables, temperature units. Let's go to the pressure. Pressure is, as you know, force per area. Then we have a lot of and various pressure units. For example, 1 bar, Pascal, Newton per square meter, milli mercury, or feet water, and pound force. It's not just pound. In the number related variables, you have met pound as the mass unit. That is called pound mass. This is called pound force per square inch. This unit is popularly called psi because pound per square inch or atmospheric pressure. This is the equal relationship. I mean, 1 bar is equal to 10 to the 5 Pascal, is equal to 10 to the 5 Newton per meter square, is equal to 750.062 milli and so on. This equal relationship can be used as the conversion factor to convert one unit into the other unit. So I have presented one group of the equal relationship and the second group of equal relationship. So let me convert one unit into the other unit. Here is the 5.075 bar. And then I'd like to this value into the unit of milli Hg. How can we convert it? So let's start with the first group. So my objective is to convert bar into milli Hg. So I want to use this equal relationship. Okay, 1 bar is equal to 750.0662 milli Hg. And then let me place this milli Hg value into the numerator, and the bar value is going to the numerator. This value, including the unit, is equal to this value, including the unit. So it means this value divided by this value is equal to 1. So this one is equal to the right hand side value because this is just 1 without any unit, right? This is called conversion factor. Conversion factor should be always just 1 unit. Then let me check the unit first in this calculation. So here's bar and here's bar. You can kill them to each other. Then what we have in the final answer is milli Hg. And then after calculation of the value, like 5.075 by 750.062 per 1 is going to the value. So we have the final answer. You know, what I'd like to emphasize is that Of course, you should calculate the values. However, you should calculate the units. Let's go to the second calculation. Of course, I have the same value as the first one. Let me change the pen to pointer. And the same value, but I'd like to use the equal relationship from the second group. Then where is the millimilli Hg? 750, a little bit different from the first one. And what is the bar? Here is the bar, 1.01325 bar here. And then after killing bar and bar, so you have the same millimilli Hg shown in the previous calculation. And then it's time to calculate the numbers. Of course, the values are a little bit different in the conversion factor, but it should be the same. So anyway, after calculation of all values, then you have found the same answer. Let's go to the third calculation. So I wanna use a two-step calculation. Let me assume that there are no relationship between bar and millimilli Hg. So we cannot convert the bar into millimilli Hg directly. So I want to use several different units. At the first step in this third calculation, I want to use the conversion from bar to psi first. So where's the psi? Okay, here. So this value is going to the numerator and this value is going to the bar. Those two values are equal to each other, so this conversion factor is equal to 1. Then you could obtain the psi value because bar is erased with another bar. And then psi. In the second step, I want to change the psi into millimilli Hg finally. Then I want to get those relationships from the first group. Anything is okay actually. So 14.5 psi here and 750 blah blah millimilli Hg here. And then finally you can erase psi with the other psi. Then in the answer you could keep the only millimilli Hg. So the unit is right. And then after calculation, this value by this value per this value by this value per this value is going to the same answer. This is the way to convert one unit to the other unit. Again, use conversion factor, which should be just 1. You can get some numbers from the equal relationships. Let's go to the other variable, process variable. Here is the volume related variable. Of course, volume is the cubic length. We have a lot of units here and there, and also we have 4 groups of equal relationship. You could use this one as the conversion factor. Just let me check those things. Cubic centimeter, or sometimes called cc, is 1 milliliter or liter, and fluid ounce is used, which is used in USA, so called fluid ounce. Going to cubic inch or gallons US or cubic feet. For the fluid ounce and gallons, I have put the US after the unit. Why? Those units are used in US and UK, United States and United Kingdom, I mean British or England. They are using apparently same units like fluid ounce and gallons, but the quantities are different. For example, here is the gallon. Here is the 1 US gallon, which equal to 3.785 liters. However, the gallon used in UK, so-called imperial gallon, is 4.546 liters. So they are different to each other. So you put US or imperial. The other thing is gallons also. We have US gallon or an imperial gallon like that. Okay, here is the one example of the conversion of one unit of volume to the other unit. Gallon to cubic yard, and I want to use or I want to find the conversion factor to correlate between gallon and cubic yard. Fortunately, we have here. So this value is going to the numerator and this value is going to the denominator, and then finally you could find the value. Please be sensitive the unit. After killing gallon, then you could get cubic yard. I'd like to emphasize again the conversion factor. Conversion factor should be 1. So we have used this equal relationship. This value gallon is equal to this value cubic yard. You should think about the unit, and then let me replace this value with unit into the right hand side of the equation. Then 1 is equal to this value per this value including units. So this one is 1 conversion factor. Then 20 gallon should be equal to 0. Cubic yard because this conversion factor is 1 without unit. We are still on the volume related process variables, and there are additional volume related variables are here. Specific volume indicating volume per mass. The other thing is molar volume per moles, similar to each other. And then the inverse form of those two values are going to specific density and molar density. So mass per volume and moles per volume. So the second law is the inverse of the first law. Okay, so let me touch some values. Here is the case for water at 4 Celsius degree, and mass density or specific density. Specific means divided by mass or mass. So mass related. Specific density is equal to this one, pound mass per cubic feet. And then from this value you could calculate the specific volume. 1 over 62.43 pound cubic feet is going to this value, and also the unit should be inversed, right? So you practically you calculate the values, but you should calculate the units. Also, by using this kind of information, you can convert from mass to volume, or volume to mass, or moles to volume to moles. Here is the case. 234 pound you have, maybe water. And then what is the volume of this mass? So here is the density, specific density. So mass per density is going to volume. Let me check the unit. So also in addition to the values, the unit should be calculated. Pound per pound, so you can kill them to each other. So feet scale is going up, so you have not feet scale, cubic feet here. Okay, something like that. Let's go to the other term, specific gravity. So specific gravity is defined as the density of species I at a certain temperature with respect to the density of water at 4 Celsius degree. It is called specific gravity. And what is the dimension of specific gravity? Of course, nothing, because it was defined by density per density, so dimensionless. This, this can be interpreted as the relative density with respect to water at 4 Celsius degree. Here is one example. The specific gravity of liquid benzene is reported as 0.8765 with subscript 20 per 4. What does it mean? Indicating that this is the specific gravity of benzene at 20 Celsius degree. Per indicates relative to. Per or relative to liquid water at 4 Celsius degree. So liquid water at 4 Celsius degree has a density of 1 gram per cubic centimeter, of course. And then the density of benzene at 20 Celsius degree is therefore just this value, 0.8765 gram per cubic centimeter, because the density of liquid water at 4 Celsius degree is 1.00 gram per cubic centimeter. The other volume related variable is density. Okay, you have learned about the related gravity density, a specific density. So I want to have several comments about the density in this slide. Density is changing with temperature, sometimes pressure. The temperature or pressure dependency of density is also depending on the phase of the corresponding materials. So we could have three different phases, and solid, nearly independent of temperature and pressure. You have a stone here, and then you have heated the stone. Do you think you would observe the volume expansion in solid? No, I don't think so. How about pressure? Please push the stone with your weight. Is there any changes about the volume? Nothing there. So solid nearly independent of temperature and pressure. Of course, at very high pressure, the solid volume is changing a little bit. In that case, I mean at high pressures, sometimes you should consider the volume change. Liquid, nearly independent of pressure, but somewhat dependent on temperature. So practically, you should think about temperature dependency of density. Our gas, strongly dependent on both pressure and temperature, of course. You are very accustomed to ideal gas law, PV is equal to nRT. By reshuffling, you could find this form. N per V, what is that? Moles per volume. Molar, no. What is that? It is molar density, right? Molar density. Or 1 over the molar volume. So it is a kind of density. And then is equal to P per RT. Ideal gas law is saying that the density is strongly depending on pressure and temperature. Okay? R, of course, is the ideal gas constant. And the values of R is different depending on the unit. Various units are there. Maybe you are very accustomed to this value, 0.082 atmospheric pressure atm liter per gram mole K. However, if the units are changing, the values are changing. Okay, and here are two comments about this dependency, especially gas. Sometimes you have met this word STP. What is the STP? Standard temperature and pressure, which means 0 Celsius degree and 1 atmospheric pressure. Okay, so the specific molar volume of one ideal gas at STP is 2.4 liter per gram mole. Maybe you know. So just put 0 Celsius degree into T, but not 0. Instead of 0 Celsius degree, you should use the Kelvin or Rankine, right? So 273.15 Kelvin and 1 atmospheric pressure here 1, and R should be used, which is this value, this unit right there, atm Kelvin. Then you have obtained this value, 2.4 liter per gram mole. So at STP, the 1 gram mole have 22.4 liter volume. So memorize this number, sometimes very useful. Okay, we didn't say about yet concentration as the volume related process variable. So concentration is mass of a solute. I have said solute per volume of solution. Solution consists of two things, solute plus solution. So volume of solution means the total volume of the mixture including solute and solvent. So the unit would be moles per cubic centimeter or something like that. Here's an example. A gas at 100 Celsius degree and 3.5 atmospheric pressure has a specific gravity. It's like that. How can we calculate it? By using ideal gas law. So moles per volume is molar density is equal to P, pressure, 3.5, and some unappropriate ideal gas constant with temperature. Temperature should be inputted in the unit of Kelvin, not Celsius degree, as you know. Then answer. At STP, you should change the value of pressure and the temperature at 1 atm 0 Celsius degree. Okay, this is the last process variables, which is time related variable. Representatively, we can imagine the flow rate as the time related variables. So mass flow rate could be used for your process design in the some picture of designing process, and molar flow rate or volumetric flow rate. Anything could be used for the process diagram. Example, the mass flow rate of a process stream is 105 point oxygen per minute. So mass flow rate here. The molar mass of oxygen is 32 gram per mole, 1 gram mole. Right, you know that. The gas follows the ideal gas law. This is the assumption. Anyway, we could use very complicated the equation of state instead of ideal gas law, but in this course we'll use the ideal gas law for gases. It means we have assumed that the all gases is working depending on the ideal gas law. My question in this example is, what is the volumetric flow rate? So we should convert the mass of gas, oxygen gas, to volume. So what kind of things we need to have? So maybe ideal gas law. So by using the ideal gas law, we could calculate the molar volume or molar density. Then we could convert the mass or moles into the volume. So here we go. The starting point is here from the question, 105 pound oxygen per minute. Here, and then I want to change the pound to gram because molar mass or molecular weight is given to us in the unit of gram and gram mole. So after getting the mass in gram, then we could convert to the volume. Anyway, so let me change my pointer to pen, and then I have applied this conversion factor. 453 gram is equal to 1 pound here. Then we can kill this one. So right now we have gram per minute. And then it's time to convert gram to gram mole. So molecular weight here, 1 gram mole, actually the inverse of molecular weight. 1 gram mole is equal to 32 gram. So we can kill the gram to gram mole. And then right now we have gram mole per minute, molar flow rate. And then by using the ideal gas law, we can change the moles into liter. So I have said at STP. Okay, so this question is about at STP, even if I didn't mention about the temperature and pressure. 1 gram mole or at STP is equal to, or have 22.4 liter as a volume. So we could use this kind of a conversion factor because 1 gram mole is equal to 22.414 liter. So here, then right now liter per minute. If we want, we could change the minute to second. 1 minute is equal to 6 seconds, 60 seconds. Then this is another conversion factor, right? Time conversion factor. Then the minute is erased with another minute. Then we have second. So the the final unit is liter per second. And then, okay, in the answer you can find cubic centimeter per second. So we need to have one more conversion factor. So 1 liter equal to, as you know, 1000 milliliter. And 1 milliliter is 1 cubic centimeter, sometimes called cc. So I can say milliliter is going to centimeter cubic. So then you can find this value. So until now in subchapter number 2, you have learned about the process variables, and it's time to go to the flow diagrams to describe the processes. Okay, here is the subchapter 3 of chapter 2, chemical process flow sheets, or equivalently flow diagrams, shortly FD. The FD, or flow diagrams, is compact and precise diagrams that present a large amount of technical information about chemical processes, which could be considered as a language that chemical engineers use. Here are 3 major flow diagrams. The first one is IOFD, input, output, flow diagram. The second one is block flow diagram, shortly BFD. And the third one, the most complicated one, is process flow diagram, shortly PFD. Here is the ammonia synthesis, and this ammonia synthesis process is an entire process. This single entire process consists of several units, multiple units, like reactor, separator, something like that. And also, Your reactor could be a batch or continuous stirred tank reactor or a PFR and so on. So I can describe a single process as three different levels. The first one is overall process. The second one, functional unit level. The third one, detailed equipment level. Each flow diagram corresponds to each level. So, input-output flow diagram is to describe our process in the level of overall and entire process. So, the required information for making the input-output flow diagram is about input, which is raw materials, and output, which is products, and the relationship between input and output, which is the reaction stoichiometry. Again, three things: input, output, the relation between input and output for IOFD, which is the entire process level. Let's go to next one, and the most popularly used one, block flow diagram, which is in the unit level of the process. So the information is required for making BFD is everything above plus material balance equations, or major process units, I have set to unit, and process unit performance specifications. So PFT is to describe the process in terms of units. The most complicated one is PFD, process flow diagram. We have the information about everything above plus energy balances, process conditions such as temperature and pressure, and major process equipment. I have said equipment specification, so which is going to the detailed equipment level. So we have three different flow diagrams. Actually, they are similar to each other, only complexity is a little bit different. So IOFD, BFD, PFD are there for the flow diagrams. This picture is about process flow diagram, including everything in this information. Okay, then here is the input-output flow diagram, shortly IOFD. I'd like to give you a more detailed explanation about each flow diagram from now on. IOFD have only single block presenting all of the physical and chemical operations in the process. So we should have a single block, and then lines with arrows represent material moving into and out of the process. So input is introduced into the process, and the output or product is going out of the process. Practically, input or raw materials enters on left, and then products leave on right. This is the practical convention. And raw materials and product flow rates or quantities may be shown on the input stream and also output stream. Here is a detailed examination about ammonia synthesis. This single block represents the entire process about ammonia synthesis. And on the left side, you have three different reactants: methane, water, nitrogen. Also, the corresponding flow rates are given to you in this input stream, like 350 tons methane per day. Also, the same thing on the right side of product line. So 1,000 tons ammonia per day, which is desired product. That is the input-output flow diagram, shortly IOFD. And okay, it's time to go to block flow diagram here. And block flow diagram is very similar to the input-output flow diagram, actually the same. But In this block flow diagram, we are trying to describe the whole process in terms of units. So you could find a lot of blocks and arrows, and each block is connected to the other block. That is the block flow diagram. Two main components, like in the input-output flow diagram. Block indicates process unit, and line with arrow process stream. So here's an example. This is a part of block flow diagram. Of course, in the entire block flow diagram, you can find this kind of things a lot, and they are connected to each other. Okay, let me check the reactor. In this case, oven. It is oven. So raw chocolate chip cookie dough is introduced into oven as a reactor, and then as the product you could get the baked chocolate chip cookies. This is a part of block flow diagram. Now let me read this text, but there are nothing. You are uh, very understandable with some example in following slides. So chemical processes are represented as a group. I have said group means a multiple number. A group of connected blocks or process units. I have emphasized the units for block flow diagram because block flow diagram is in the level of a unit. Each process unit represents a specific process function in which materials undergo chemical and/or physical changes, like reactor, mixer, something. Lines with arrows connect the blocks and represent process streams, input and output. Raw materials enter on left and production leave on right, like in the input-output flow diagram. Quantities or flow rates of inputs and outputs may be indicated either directly on the diagram or sometimes in an accompanying table if you don't have any space in the picture. Four kinds of process units, important thing. Mixers, reactors, splitters, separator. We'll use those four different process units in the block flow diagram. Okay, here is four process units. The first one is mixer. Mixers is the unit operations to combine multiple inputs into a single output. Here is an example, the mixer, and I am introducing butter, sugar, eggs, flour, sodium chloride, and sodium bicarbonate, plus chocolate chip into the mixer, and then the single output contains raw chocolate chip cookie dough, right? So the characteristics of mixer is to have multiple input and single output, which is the mixer. Let's go to the reactor. The input streams contain reactants, of course. Multiple chemical reactions take place inside the reactor. The output streams contain reactor product as well as unconsumed reactants. So, okay, okay, here's the reactor I have said about it, the oven, and the raw chocolate chip cookie dough made from the mixer is introduced into the reactor. Then finally you can get the baked chocolate chip cookies. That is the reactor. And let's go to the number 3, splitters. Okay, number 3 splitters and number 4 separators. They have a lot of similarity. However, you should distinguish the separator from the splitter. Okay, splitters is the unit operation to split. I have said split a single input into 2 or more outputs. Of course, this is the splitter. So usually you should have multiple output streams, and typically only one single stream is introduced into the splitter. If the input is a mixture of two or more components, then the output streams of a splitter all have the same composition as the input. Okay, so here's an example. 4 dozen cookies with 75% chocolate chip cookies and 25% peanut butter cookies. So this is the amount of input, and those information are the compositions of the input. And then let's split it into two streams. What happens? 4 dozen cookies is going to the 3 dozen cookies in the first stream, and 1 dozen cookies is going to the stream number 2. And also, you should concentrate on the composition. So the composition of the first stream is 75 to 25%. How about the second output stream? 75, 25. So both of the output streams compositions are the same as the composition of the input stream. So splitter didn't touch the compositions. However, the splitter changed the amount. So again, I'd like to say splitters is the unit to control quantity, not touch the composition. Okay, keep in mind, splitter doesn't touch the composition. Let's go to the next one, separators. In these separators, a single input stream is separated into multiple outputs. Actually, at this point, separators are the same as splitters. The outputs have different composition from each other and from the input. So it is the very important point. Okay, so maybe you can understand exactly from the example. Okay, the same input, 4 dozen cookies, 75% chocolate chip, 25% peanut butter are introduced into the separator. And then we have two streams on the output. 3 dozen, 1 dozen, the same as that of the previous splitter case. However, look at the composition. The composition of the first product line or stream is 98% chocolate chip cookies and just 2.8% peanut butter cookies. So the composition of chocolate chip and peanut butters are changing from 75 to 25 to 98, well actually 97 to 3 composition. Okay, so the stream number 1, the output stream number 1 is chocolate chip dominant. Let's go to the other stream, like the second stream, output stream. So 1 dozen cookies, okay, the amount is the same in the first case. However, look at the composition. 92% peanut butter cookies are obtained in the second output stream. So the output stream number 2 is peanut butter dominant. That is the separator. So separators touch the amount plus compositions. However, splitters can touch the amount but not compositions. Please try to understand how to distinguish between splitters and separators. Anyway, we have this kind of 4 process units which is used in describing block flow diagrams. Okay, so this is one example of the complete block flow diagrams. So this is about the ammonia synthesis the process, and this is the main reactor for making the ammonia by using hydrogen and nitrogen. but you can find a lot of units which are involved in this process. Before the reactors, we have a lot of steps, and those units are for generating hydrogen and also getting nitrogen. So look at that, natural gas, hydrogen and carbon sources. Here actually hydrogen sources, and stream, so water, and mix together, then go to reactor, then mixer with air, then finally you have this kind of materials which can be used for making ammonia, actually for making hydrogen and also providing nitrogen. Water, carbon monoxide, methane, nitrogen, oxygen, H2. Then more reaction. Finally, all of the hydrogen in uh, the the hydrocarbons are changed into hydrogen. So right now hydrogen and nitrogen, nothing changed. CO2, carbon monoxide is completely oxidized into carbon dioxide and water. So we have H2 and N2 right now. Then go to the separator, and water is separated from the input mixture, and then separator for CO2 separation, and then only thing remaining is hydrogen nitrogen plus water impurity, and then mix it together and to the main reactor, then we could get the ammonia. Of course, in the final output stream, even in the final output stream, you could find the unreacted reactants. So ammonia is going out of the first output stream, and then the others is going back to the mixer by using recycling. Okay, it's time to go to the last and more complicated, or actually most complicated flow diagram in this the textbook. Chemical processes are represented as a connected group of process equipment. That is the process flow diagram. Actually, process flow diagram is very similar to the block flow diagram. However, you should provide detailed information about each equipment. For example, separators, we have various equipment for separating the desired product from the mixture of the others. So flash drum, cyclone, and distillation, or tray column, those things are used for the separators. Material transfer equipment would include blower, centrifugal pump, conveyor, and turbine. Okay, transfer equipment, heat exchanger, furnace, kettle type reboiler, and evaporator. So we have a lot of choice for the four main units: mixer, reactors, splitter, and separators, something like that. So we'll use this equipment for making the flow, no, the process flow diagram, or PFD. This is the process flow diagram for ammonium synthesis facility. So a lot of equipment are presented in this PFD. Let me check the comment about this process flow diagram. All major pieces of process equipment are drawn representationally. Let me say, here is the ammonia converter as the reactor, and heat recovery, where CO2 stripper, which is the separator, or something like that. Reactor type and separation methods have been chosen. Included is equipment used to move material around That is to say, pumps, compressors, conveyor belts, and to heat or cool material, like heat exchangers and furnaces. Generally, gas streams are at the top, like at the top, and liquid streams are in the middle, and then some solid streams are toward the bottom, something like that. Not always, but it is a kind of practical convention. The flow rate or quantity, composition, temperature, pressure, and or phase of process streams are indicated, usually in an accompanying table. So, this PFD looks very complicated and we don't have enough space inside of the picture, right? So usually we will use the accompanying table. Then in the table you have list some details about each equipment. That's the PFD, process flow diagram. Okay, we are again back to the very first table where summary about these three major flow diagrams. Again, IOFD, BFD, and PFD look similar to each other actually. So, input-output flow diagram is used for initial screening of process economics by considering only the difference between very first product no, very last product and very first raw material cost. Okay, the BFD, the most popularly used in this class. So it is for deciding the required process operations and alternative process schemes. And the last one, PFD, process flow diagram, is for preliminary estimates of capital and operating costs. That is the flow diagrams. You are still on this of chapter 3 of chapter 2. The first part of this subchapter 3 was devoted to the flow diagrams. So you have learned about three different flow diagrams to describe your process, your chemical processes. Then right now I'd like to discuss about the process operation mode. Three process operation modes are there, which are batch mode and continuous mode and semi-batch mode. So let me start with the batch mode of a reactor. Here is a chamber, like a beaker, and then some agitator to mix reactants. And then at time equal to 0, I'd like to pour all of the reactants A and B into the chamber and then close the cap. Again, input streams enter the process unit all at once and then start the reaction. So 1 hour later, 2 hours later, 3 hours later, reaction goes forward. And at the same time, maybe A is reacted with B to produce the component C. And then at time equal to 3 hours, open the cap and then get all products and reactants from the chamber. That is the batch operation mode. So let me check the concentration profiles along time. At time equal to 0, we have some concentration of A and B. Maybe let me say 1 mole of A and 1 mole of B. And this value would be maximum value because they will be consumed a long time. Of course, at time equal to 0, there are no products C. However, over time, the amount of A and B in the reactor decreased over time, right? Something like that. And then also, at the same time, the product C would increase over time. At time equal to 3 hours, output streams are removed from the process unit all at once. So, here's the most important characteristic of the batch process operation mode. What is that? Concentration of reactants and products are changing along time. Or I means the concentration is showing the time dependency. It is most important thing. That is the batch mode characteristics. Here are more comments about the batch mode. And input and output streams are quantified in dimensions of mass or moles, the amount, instead of mass per second or moles per minute, or like flow rate. Because I will pour all of the reactants at time equal to zero. Everything is there. And then the important thing is the amount itself, not the flow rate. And also during reaction, there are no flow into the system or out of the system. So instead of the flow rate, we will use the dimension of mass or moles for quantification in the batch reactor. This batch mode is used in pharmaceutical, specialty polymer, and personal care products. They are a little bit expensive products. And the bad thing of the batch mode is its low annual production rate, like from 50 to 500 tons per year, very low. The good thing is this batch equipment can be used for different products. So today I'm producing some alcohols from my batch reactors, and then tomorrow I could change the product from alcohol to another one. Okay, so that is the batch mode. The next one is continuous flow process mode, and the same chamber. However, even at time equal to zero, A and B are introduced into the system at some specific flow rate. At the same time, the product C is going out of the system. And after 1 hour later, the same situation, 2 hours, same situation, 3 hours, same situation, and it is going forward. So, the concentration profiles of A and B and C is like that. C is some value, A some value, B some value, which is not changing a long time, because even at time equal to zero, the the each concentration of each reactant and product is on the steady state. So the most important characteristics of continuous flow process is time independency of concentration. The dashed line indicates the profiles of batch reactor. There are big difference between the batch mode and continuous mode. Input and output streams are quantified in dimensions of mass or molar flow rate. For the continuous flow reactors, we should use the flow rate instead of just the amount, because we are introducing something continuously, we are getting something continuously. So instead of amount, we need to characterize the streams by the flow rate, like mole per second, the kilogram per minute, or something like that. These continuous processes are used in petroleum and industrial chemicals, the mass production chemicals. Annual production rate is very large, like 1,000 to 5,000 tons per year. But the bad thing is the equipment is dedicated to a single purpose for only one chemicals. Okay, next one is semi-batch process, which is a combination of batch and continuous process. So here is the situation. The chamber, and then I'd like to pour all of reactant A at time equal to zero. Looks like a batch reactor. And then after time equal to zero, I am feeding the other reactant B continuously during 1 hour, 2 hours, 3 hours. And then at the end of the reaction, we'll get all of things after this continuing the flow of B. So from the viewpoint of B, reactant B, this is a kind of continuous reactor or process. However, from the viewpoint of A and C, this is the batch reactor. So it is called semi-batch processes. Again, we have three modes introduced in the latter part of this subchapter. The first one is batch mode, second one is continuous mode, and the third one is semi-batch mode. Okay, so one more slide for this subchapter. Any of the process units like mixers, reactors, separators, splitters can be operated as batch or continuous or semi-batch, even if I gave you an example of reactors. In a process flow diagram, it's possible to have mixed modes of operations. Several mixers in one single PFD would be operated at batch. However, at the same time, the other reactors or the other mixers could be operated in the semi-batch mode or something like that. Steady state versus transient or unsteady or non-steady state. So as you know, continuous process was starts at the steady state. So what is the meaning of steady state? Time independent state is called steady state. In the time independent steady state, process variables do not change with time, like in the continuous process. Okay, here, continuous flow process case. Product quality is more constant and operating costs are generally low, so it can be used for the mass production. However, unsteady state conditions was met on the batch reactors, right? One or more process variables changed with time, right? Concentration of A and B is going down a long time. At the same time, concentration of C as a product is going up. Batch and semi-batch processes is belonging to this unsteady state, the reactors or separators or mixers. That's it for the subchapter 3 of chapter 2.